Today everyone, for task 1 we are applying differential equation methods to analyze population growth in Australia. Our study covers a 20-year window, starting from the 2006 census through to our current year 2026.
Exactly. Australia is a fascinating case study with a population now approaching 27 million. It's a prime example of how demographic trends can be modeled using classical mathematics.
To do this, we are utilizing the Malthusian model, first developed by Thomas Malthus in 1798. The core idea is simple. The rate of growth is directly proportional to the number of people already in the population.
In other words, the more people there are, the faster the population grows. The relationship is expressed through a first-order differential equation, which you can see from the slide here.
Today, I will be presenting the data in this table, which illustrate the population of Australia from 2006 to 2026. Moving forward, we can see a consistent upward trend. By 2010, the population had already grown to about 22.05 million, showing that Australia experienced a steady population growth during the period. As we continue through the table, the population keeps increasing each year. In 2015, the population reached approximately 23.82 million, and by 2018, it had grown further to about 24.96 million. Okay, looking at the more recent years, the population exceeded 25 million in 2019. After that, it continued to rise gradually. For instance, in 2022, the population was around 26.20 million, and in 2024, it increased to approximately 26.71 million. Okay. Finally, according to the table, by 2026, the population of Australia expected to reach about 27.3 million people. In conclusion, the population of Australia has grown steadily from about 20 million in 2026 to over 27 million in 2026.
To model the population growth of Australia, I use the exponential growth formula. P equals to A exponential to the power of KT, where P is the population, A is the initial population, K is the growth constant, and T is the time. First, I set the year 2006 as P equals to 0 with a population of 20.4 million. Substituting into the formula, I obtained A equals to 20.4 million. So, the model becomes P equals to 20450966 exponential to the power of KT. Next, I use the population for the following year, 2007, which is 20.8 million, to find the value of K. After solving the equations and applying the natural logarithm, the value of K is approximately 0.0182. Therefore, the final exponential model is Pt equals to 20450966 exponential to the power of 0.0182t. This expression can be used to estimate Australia's population growth over time.
Now, let's move on where we use our particular solution to predict a future value. For the model, I have chosen the year 2030 since our starting point is t equal to 0. The year 2030 corresponds to t equal to 24. By substituting t equal to 24, we get our equation. After calculating the exponent and multiplying it by our initial value, the predict population for the year 2030 is expected at approximately 31,652,911. This shows a steady growth trend based on our differential equation model. Next, we look back at our past value to see how well our model aligns with previous data. I select the year 2016, which corresponds to t equal to 10 in our timeline. Using the same particular solution, we substitute t with 10. The result for the year 2016 is 24,533,269. This calculation allows us to verify the consistency of our growth model across different points in time, moving from the past toward our project future.
Now let's look at the visual data for Australia from 2006 to 2026. We have broken this down into two specific views. First, this graph shows the actual population data starting in 2006 at approximately 20.4 million. You can see a steady linear like a climbing graph. This point represents the real-world census figure and official estimates leading up to the present day. Next, we have the multi-gen model curve. This is the mathematical idea generated by our differential equation. Notice the distinct J shape of the curve. This represents exponential growth, where the population increases faster as the total numbers of people grows. By comparing the two, we see the multi-gen curve provide an excellent fit for Australia's trajectory, accurately projecting us toward the 27.2 million mark by the end of 2026.
It's different, right? Anyways, I will move on to the analysis questions. Question 1. Are the values calculated from the particular solution consistent with actual values? My answer is yes. The values obtained from our calculation are consistent with the actual population values of Australia. It's because both the estimated values from our calculation and the actual data show a steady increase in population over time. Alright, question 4. What factors have influenced population growth in the past? There are several factors influencing Australia's population growth in the past. Firstly, immigration, as Australia is one of the most popular destinations for immigrants around the world, followed by economic growth and healthcare improvements and rapid urban developments, as major cities such as Sydney, Melbourne, and Brisbane have expanded and attract more people for jobs and education opportunities. Now, on to the last question. What factors may affect population growth in the future? In the future, several factors may influence the population growth of Australia. Firstly, economic opportunities. A strong economy may attract migrants who are eager for job opportunities and encourage more population growth. Secondly, environmental factors. Climate change and resource availability may affect where and how people live. And thirdly, technological and healthcare advancements. Improved healthcare may increase life expectancy and therefore increase the population size of Australia. That'll be all.
From our analysis, we calculated the percentage error for the population of Australia in 2017. Based on our calculation, we calculated the difference between the actual value and the estimated value, which is 59,319 people. After applying the percentage error formula, the percentage error is 0.24%. Even though the difference seems large, it is actually very small compared to the total population of more than 24 million people. This means the estimated value is very close to the actual population. The small difference may happen because population estimates are calculated using statistical models based on previous census data, birth rates, death rates, and migration trends. Unexpected changes in migration or natural population changes can also affect the final number. In conclusion, the percentage error of 0.24% shows that the population estimate for Australia in 2017 was highly accurate and reliable.
To sum up, we successfully achieved the objectives of this assignment by using differential equations. In task 1, we focus on the population of Australia over 20 years, from 2006 to 2026, using first-order differential equations. Then, we use MAT099 model to estimate the population. In the data analysis and discussion, we presented a graph comparing the actual and estimated population values over the 20 years. From the calculations, we observed that the population shows an increasing trend, as seen in the graph.